Hello students, so let's do the revision of a chapter solution. How we are going to go ahead with this topic is that we'll be taking one examples and we'll be explaining you the concepts. So when we talk about the solutions, there are concepts like first concept is concentrations of solution. Like we'll be discussing about the molarity, mole fraction, mass percentage, weight percentage. Okay, this is the thing. And after that, solubility of gas in liquid, solubility of gas in liquids. Right. We are going to discuss about the Raoult's law, third Raoult's law. Then fourth is ideal and non-ideal solution. Ideal and non-ideal solution. Also, we'll discuss about the colligative properties and abnormal molar mass. Okay, we'll take one question. First question will be based on a concentration of the solution. Okay, this question, the density of 2 molar aqueous solution of NaOH is 1.28 grams per centimeter cube. What is the molality of the solution? See, molality means what? How do we define? Let's define this first. Molality is what? Number of moles of solute upon mass of solvent in kg. Right? Somehow I want number of moles of solute and I want mass of solvent in kg. Now what is the data which is given? The data which is given, what they are saying is the solution is 2 molar. The solution is 2 molar. 2 molar means what? It is capital M. 2 molar is equal to 2 moles per liter. Remember, this capital M describes the molarity. Molarity means 2 moles per liter. That is what is the data given. And density of this solution, whole density of that solution is what? 1.28 grams per centimeter cube. Now, what is the molality? See, if I want to know what is the molality, number of moles of the solute, I know that it is number of moles is 2 moles. This is what I know, right? Somehow I want a mass of the solvent. Now what is a solution? If you see, a solution is a solute plus solvent. If I know the mass of solution and mass of solute, then I can easily get the mass of solvent. Right? Means if I rearrange this solvent, I'm just writing solvent mass. Okay, or we'll write it this way. Mass of solvent is equal to mass of solution minus mass of solute. What is the solute over here? Solute is NaOH. Remember that solute is NaOH. And solution is together NaOH and a water. Aqueous solution. Right? It is mentioned aqueous solution. That's why I am saying that it is a water. Now, how do we get the mass of the solution? Because they have given a density of the solution to be 1.28 grams per centimeter cube. Therefore, what do we know about the density? Density is equal to mass upon volume. Therefore, mass will be is equal to what? Density into volume. Right? So, what will be a mass of solution? Mass of solution is density of the solution. How much is that? It is 1.28 grams per centimeter cube multiplied by volume. How much is the volume? See, it is 2 moles. Aqueous solution is 2 molar. Means what it is? 2 moles per liter. Means that is 1 liter. volume is 1 liter. So this is in centimeter cube. So how do we write a 1 liter? 1 liter is equal to 1000 ml, which is equal to 1000 centimeter cube, right? So I am writing this over here, that is 1000 centimeter cube. So this per centimeter cube gets cancelled. What remains is 1280 gram is the mass of the solution. So what I'll do is I will substitute it over here. In this, mass of solution is 1280. Okay, we'll do this separately, mass of the solution. Now second thing, I need to find a mass of the solute. Now what is the mass of the solute? How do we get a mass of the solute? Now to find mass of solute, what is that solute? NaOH, right? See, if we have the number of moles, we can easily find the mass of the solute. Like how the number of moles is given? Number of moles is given to be weight upon molar mass, right? Therefore weight of the solute will be what? Mole. This is, I'll write weight upon number of moles is weight upon molar mass. Don't get confused with molarity. We'll write it mm. Let's say molar mass is mm I'm taking. Okay. So weight of the solute will be what? Number of moles multiplied by molar mass. So what is the number of moles of the solute? Number of moles of the solute, it is 2 mole, right? 2 moles. And what is the molar mass of NaOH? Molar mass of the NaOH, if we calculate, NaOH comes to be how much? Molar atomic mass of sodium is 23, oxygen is 16, plus hydrogen is 1. So this comes to 40. So this is 40. So this is 80. So I got the weight of the solute. To find the mass of the solute, so I'll just clean this part. You can copy this. So this is equal to what? 1280, no? 1280 minus 80, which is equal to 1200. Right? This is the mass of the solvent. Now substitute it in this formula. I'll clean this also. I'll just clean this also. Substitute in this formula. That is, number of moles is what? 2. And mass of solvent is what? 1200. That is in grams, right? Whenever this is in gram, you want mass of solvent in kg. Either you multiply 1000 over here, or you write this in kg like 1.2. Isn't it? Either you multiply this 1000 or write it as a 1.2 kilogram. Isn't it? One of the things you can do this, and this and this will get cancelled. 2, 6, 2, 5. Right. So this is 10 by 6. So 1.66 moles per kg is the answer. 1.66 moles per kg is the answer for this. Next question. Next question is 6.023 into 10 raised to 20 molecules of urea are present in 100 ml of its solution. What is the molarity of the solution? See, when do we find the molarity of the solution? What is the formula? Molarity, it is represented by capital M, is number of moles of solute divided by volume of solution, in liter. This is what the molarity is. Now this question, like, many students must be searching for what? Number of moles I need to find. Means we know this formula, right? Number of moles is equal to weight of the given weight upon molar mass, right? Given weight, number of moles is, this is the formula, given weight upon molar mass. But here, what is the question? Question is said that 6.023 into 10 raised to 23, 20 molecule, not 23, 20 molecules are there. There is weight of urea is not given, also molar mass is not given of the urea, but still you can find the molar mass, but weight only is not given. Can we use this formula to find a number of moles? No, we cannot use this formula, but we can use one logic. As per the concept, what is 1 mole is equal to? 1 mole is equal to how many? Like 1 mole of anything is equal to how much? 1 mole is equal to, it is 6.023 into 10 raised to 23. Like I say that 1 mole molecule means what? 6.023 into 10 raised to 23 molecules of urea. If I say that 1 mole atom, then it is 6.023 into 10 raised to power 23 atoms, right? If I say that 1 mole of these hairs, okay, then what it is? It is 6.023 into 10 raised to 23 hair. So basically, that many hair I won't be having. It is a very big number. 6.023 10 raised to 23 is very big number. We cannot use it for counting hairs or dealing like give me 0.0001 dozen 0.0001 moles of banana or apples, because that is very big number and calculation will become more and more complex. But we can definitely use moles for what? Atoms, molecules and the ions, because in a small quantity they are in large amount, right? So 1 mole is equal to 6.023 into 10 raised to 23 molecules. So I need to find what is the meaning of this 6.023 into 10 raised to 20 molecules will be is equal to what? X mole. I can write, I am finding this like these many molecules means how many moles? 1 mole is equal to 6.023 into 10 raised to 23 molecule. From where I am getting this relation? I am getting it from the Avogadro's relation. Avogadro, according to the Avogadro said that 1 mole of the substance is equal to 6.023 into 10 raised to 23 molecule. So I am relating it. 6.02 into 10 raised to 20 is equal to X mole. So if I do cross multiplication, what I get is 6.023 into 10 raised to 20 divided by 6.023 into 10 raised to 23. This and this will get cancelled. What remains is X is equal to 10 raised to minus 3. Right? Means X is what? Number of moles. Means these many molecules is equal to 10 raised to minus 3 moles. Right? So this is 10 raised to minus 3 mole. And what is the volume of solution in liter? It is given in ml, 100 ml. 100 ml is just 0.1 liter. Or you can write it this way also, 100 into 1000. So what will happen? This and this will get cancelled. So this is 10 raised to minus 3. This is 10 raised to 1. This is 10 raised to minus 2 moles per liter. This is your answer. Means concentration you can further 0.01 moles per liter. This question is about the mole fraction. Question asked is a sugar syrup of weight 214.2 gram contains 32.4 gram of sugar. Calculate mole fraction of the sugar. Right? What is the mole fraction? Let's say there is a solution. Solution means what? Solution means a solute and solvent. Solute can be more than one. Let's say here there is a solute is sugar and solvent is water, right? Sugar is getting dissolved in water. That is what is sugar syrup, no? So sugar and water. The question is mole fraction. To find the mole fraction, let's say I am writing mole fraction of the sugar is number of moles of sugar. I need to find this upon total number of moles of all the things, like number of moles of sugar plus number of moles of water. And what is a mole fraction of what solvent? That is number of moles of water divided by this total number of the moles, that is number of moles of sugar plus number of moles of water. To find the sugar, mole fraction of sugar, I need number of moles of sugar as well as number of moles of water. Now the question is, sugar syrup total weight is 214, means solution is how much? 214.2 gram. This is the weight of the solution. I want the weight independently. Contains 32.4 gram of sugar, means this contains 32.4 of the sugar. Now what is the solvent? What is the weight of the solvent? Right? Subtract from this 214.2 and this is 32 point, I guess it is 34.2. 1 minute. Yeah, this is 34.2, not 32.4. This is 34.2. So this is 34.2. My calculation will become easy, right? 0, 0, and 11. This is 8. This is 180. Means you're getting this to be 180. Clear? We have the masses of the solute and the solvent. We also have the molecular formula of the sugar, so that is solute, right? We can easily find the molar mass of that, isn't it? So first we'll find number of moles of sugar, that is N sugar. So for that I require a molar mass. Molar mass of sugar is how much? C12 H22 O11. This is given, means 12 into 12 plus 1 into 22 plus 11 into 16. Right? So this is what? 12 into 12, 144 plus 22, and this is 11 into 16 is 176. Yeah, 176. If you add this up, 144, 20 and 176, this comes to how much? 6, 7, 7, 14, 342. Nice value. Why I am saying this is to be nice one? 342 grams per mole. This is what the molar, because this is 34.2, no, some decimal. I don't need to use a calculators or logarithm table for this type of calculations. 342. So therefore, a number of moles of sugar will be is equal to how much? Given weight is 34.2 divided by 342. See the units also. This is in grams. This is grams per mole. This gram and this gram will get cancelled. And this is what? 34.2 could be written as 342 into 10 raised to minus 1. No? And this is 342. This and this will get cancelled. Therefore, which is equal to 10 raised to minus 1. That is 0.1 mole. So I'll write it separately over here. Here I'll write number of moles of sugar I am getting to be 0.1 mole. Okay. Now, number of moles of what I need to find? I need to find a number of moles of water. Number of moles of water. N is the symbol for the number of moles of water. That is how much? A given weight. How much it is? 180. I am getting it to be 180. And divided by molar mass of water is how much? 18. So this is 10. This is 10. Right? So number of moles of water I am getting it to be is equal to 10. So let's find what is told. What is asked? Calculate the mole fraction of sugar. So mole fraction of sugar will be is equal to what? It is number of moles of sugar, that is 0.1, and this is 0.1 plus 10, which is equal to 0.1 by 10.1. Answer comes to 0.0089 something. That's going to come 0.09. Right? This is a mole fraction of the sugar. Now what would be a mole fraction of the water? You can easily find this way also. You can write mole fraction of the water will be 10 divided by 10 plus 0.1, 10.1. This is one way. Or we know that sum of mole fractions of the two component or the three component or any number of the component is always is equal to 1. So here you are getting 0.009, right? So that's the answer which you are getting. See, sum of mole fraction of the two component or more component is always is equal to 1. Remember that. Like mole fraction of sugar plus mole fraction of water is equal to 1. How? You do this, no? Number of moles of sugar upon n sugar plus number of moles of water plus number of moles of water. Denominator is same. Sugar plus water. So what would be this numerator? Is this, and denominator? Right? I can cancel this, which is equal to 1. Sum of mole fraction of two or more component is always equal to 1. Once you get this sugar, you can easily, although it is not asked, mole fraction of water can be is equal to written 1 minus mole fraction of the sugar. That's it. Hello students, welcome everyone to the second lecture of the revision of the solution topic. So here we are going to discuss about the vapor pressure and Raoult's law. Topic is vapor pressure and Raoult's law. Now what is a vapor pressure? Let us understand the definition of the vapor pressure. By definition, vapor pressure is written this way. Vapor pressure is a pressure exerted by vapors of liquid, pressure exerted by vapors on surface of liquid in closed system. In a closed system. For example, if I consider a water, right, I'll consider a system this way. We know that water is something which is less volatile, non-volatile. It evaporates at 100 degrees Celsius, right? We'll consider this system at a room temperature, right? Volatility. Whenever we say something is volatile means what? Evaporation takes place at a room temperature, right? So this is water. This is water. And let's say another container is there of the same dimensions and same volume over here, and this is acetone, right? So which is more volatile? We know that acetone is more volatile. It evaporates at a room temperature. So in this system also there will be certain vapors. Let's say these are the molecules of the water which exist in this empty space because of the certain evaporation, right? And here also they will be in large number. Why? Because here evaporation is more since the acetone is volatile. Now this particle are going to exert a pressure on the surface of the liquid, right? Also here also there will be a exertion of the pressure on the surface of the liquid, right? In which case the pressure exerted by the particles is more, it is acetone. Here the pressure exerted by the particles is more and here it is less. So what we can say is that vapor pressure pressure is directly proportional to volatility. Means more is the volatility, more is the vapor pressure. That is what it means, right? So now, one more thing we can conclude over here is that one thing is vapor pressure is directly proportional to volatility. Second, we can say that what is the meaning of boiling? Boiling is the temperature at which evaporation takes place, right? So we know that for this you require a higher temperature. This evaporates at a room temperature. Like that's why it is volatile. So boiling point is what? Is the temperature at which vapor pressure becomes equal to the atmospheric pressure. Is boiling point is inversely proportional to what? Vapor pressure. Keep this in mind. Means more is the vapor pressure, less is the boiling point. Here vapor pressure is more, the boiling point is just room temperature. It evaporates at a room temperature. Here vapor pressure is less, boiling point is high. It evaporates at 100 degrees Celsius. These are the 2 points you can remember regarding vapor pressure. Now coming to the Raoult's law. What does the Raoult's law say? Raoult's law says that when two volatile, I'll write here, when two volatile liquids are mixed to form solution at same temperature, partial pressure of each component is directly proportional to its mole fraction, right? This is what is a Raoult's law is. Means what does this mean? Like you consider two components, let's say A, this is a component, and there will be a vapors and it will be creating some vapor pressure due to this, and there is another component B and there will be a vapors and there will be a vapor pressure due to this component on the top. You mix them and form a new solution which is A and B. So what will be the vapor pressure? Partial. Here let's say these are the particles. I'll circle this way. These are the particles. Means here there will be a two kinds of things. In a vapor phase, here there will be a two kinds of things. Let's say this. So more the number, let's say B is more. Let's B quantity is more. So vapors of the B will be more, and a partial pressure due to B will be more. So what we can say is that over here is that partial pressure of the A is directly proportional to the mole fraction of the A. Means what? More is the mole fraction, more is the amount, more will be a more fraction, right? More is the amount of the A, it will it will contribute more to a vapor pressure over there. And partial pressure of B is directly proportional to mole fraction of the B, right? So I'll introduce a proportionality constant, that is a PA. I'll write P naught A XA, and this is what PB is equal to P naught B XP. Now what is this? P naught A and a P naught B. P naught A and P naught B. I'm talking with respect to this. These are the vapor pressures. These are vapor pressures of pure components. Pure component means not in a mixture form. Pure components A and B. Means over here they will be exerting some pressure, vapor pressure. It is P naught A, and over here it is pure. It is exerting some pressure P naught B. You just consider like P naught A. Like when it is only A, then mole fraction of A will be what? Maximum. That is 1. So if this is 1, that time what is this? PA is equal to what? P naught A, right? So there is no partial pressure. Partial pressure will be only due to its component A only. Here only B is there. Means what would be a mole fraction of the B? That will be is equal to 1. So PB will be is equal to what? P naught B. That is what it means, isn't it? So P total is what? Sum of partial pressure of A and a partial pressure of B. So P total is written, could be written this way: P naught A and mole fraction of the A plus P naught B into mole fraction of the B. This is P total. Right? Let's solve one question based on this. Okay, let's solve this question. Vapor pressure of two liquids P and Q. You also give try. Pause this video for some time and then check your answer. That will be a best way of revising this topic. Okay, so two vapor pressures of two liquids P and Q is 80 mm of mercury and 60 mm of mercury. What will be the vapor pressure of a solution obtained by mixing 3 moles of P and 2 moles of Q? Now when you mix them, how many? 3 moles of P and other is 2 moles of Q. What will be a total vapor pressure, right? Now this is 80 mm of mercury and a 60 mm of mercury. That is the unit of the pressure, which is basically used for measuring a very small amount of the pressure, right? So here, what do we write? P total. We'll write this. P total will be what? Partial pressure of A, partial pressure of B, partial pressure of A plus partial pressure of B. Partial pressure of A is given as what? P naught A, pure components, and its mole fraction, and the here product of partial pressure of B into its mole fraction. Now P naught A is given, right? If you see the vapor pressure of two liquids P and Q, P is given, that is P naught A is given to be 80 mm mercury, and Q, sorry, I mean this is P and Q, just this is P and this is Q. So this is P naught P I am writing, and this is P naught Q is 60 mm mercury, right? Now what we have this value, somehow I want a mole fraction of the P and mole fraction of the Q. So what would be a mole fraction of the P? It is number of moles of P, that is equal to how much? 3 moles, right? So it is 3 moles, and total number of the moles. Total number of the moles is what? 3 plus 2, which is equal to 3 by 5. And mole fraction of the Q is what? 2 moles, right? Q is what? How many moles? 2 moles of Q divided by 3 plus 2, and this is 2 by 5. Now what we need to do? We'll substitute it over here. Therefore, P total will be is equal to what? 80 multiplied by 3 by 5 mole fraction of the P plus 60 multiplied by 2 by 5. So we can cancel this 5 ones, and this is 30, 16, and this is 5 12. So how much this comes to? 16 3s are 48, 48 and 24. So P total will be what? 92 mm of mercury. 92 mm of mercury. Right? Sorry, not 92, I guess. 72. No? 72 mm of mercury. This will be the P total. Okay, here is the next question. See, this question is also very close to the previous one, very similar question. But here, directly the number of moles are not given. You see, if you read the question, you can give a try also to this question. Question is, at 40 degrees Celsius, vapor pressure of pure liquid benzene and a toluene are 160 mm of mercury and 60 mm of mercury respectively at the same temperature. What is the vapor pressure of an equimolar solution of the liquid, assuming that the solution is ideal? Ideal means there is no deviation from the Raoult's law, right? So here, like in the previous example, number of moles were given. Here that is not given, right? What is the thing? The word they have said, it is equimolar. Equimolar means what? Equal number of the moles. Like A is also 1 mole, then B is also, or benzene is also 1 mole, then toluene is also 1 mole. If benzene is 2 mole, then toluene is also 2 mole, right? Or benzene is 3 mole, then toluene is also 3 mole. Now in this case, we have to deal with the mole fraction. Now what would be a mole fraction when they are equal component? Mole fraction will be is equal to half. No, means for example, mole fraction of the benzene, I am considering number of moles to be x. What would be this? X plus x, because since it is not given, right? Number of mole fraction of toluene will be what? That is also x upon x plus x. Like both have equal number of the moles. So what is this? X upon 2x. This and this will get cancelled. This is equal to half. Here x upon 2x. This is also is equal to half. So mole fraction is half. So what would be a P total? What would be a P total? P total will be P naught, means pure vapor pressure of benzene, right? How much is that of the pure benzene? It is 160, and mole fraction is half, and pure vapor pressure is 60, and here also this is half. So this is what, 80 plus 30, so 110 mm of mercury. So that was a simple question which I did. Here, our topic is ideal and non-ideal solution. Ideal and non-ideal solution. So ideal solution, what is the definition of ideal solution? Ideal solution. Solutions which obeys Raoult's law over entire range of concentration, right? That is what the ideal solution. Solution which obeys solution which obeys Raoult's law over entire range of concentration. This is ideal solution. And non-ideal solution which do not obey Raoult's law over entire range of concentration, right? Right over here. Non-ideal. Non-ideal solution. When you mix two solutions, this is when we mix two solutions, it is not obeying a Raoult's law. Now, what is let's have the idea about what is the meaning of the, we'll understand graphically what is ideal solution. Like when you mix the two solutions. Okay, this is what the graph which is there in your NCRT, right? Graph is this way. Let's say this is mole fraction of the A and here mole fraction of the B. and this is 0, so this is 0.1, this is 0, right? This is 0.2, this is 0.3, 0.4, 0.5. You see mole fraction of the A I am increasing 0.7, 0.8, 0.9, and this is 1. Okay. And this side, if this is 0, then this shall be what? If this is 0, then this should be 1, because sum of the mole fraction of two components will be always is equal to 1. This should be 9, this should be 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1 and 0, right? You see, in all the cases, you add these values, a mole fraction will be is equal to 1. Over here, B component, only B component is there. So, we'll draw a graph like this, right? B components, this is the axis for the vapor pressure. This is the axis for vapor pressure. And this is the axis also for the vapor pressure, but for the other component. Hope that is coming into the frame. Yes. Right. So here XB. XB is maximum, means mole fraction of the B, means only B component is there. So what will happen as we go across here, what happens, mole fraction of the B is falling, means what we can write is that this is what the graph which we are writing. Mole fraction is falling. Like this is for a P naught, in this case this is PA, partial pressure. This is good. Partial pressure of A is going to fall in the solution, right? And let's say this is for B, means initially A, this is B, this is PB, partial pressure of B is falling, and this is A. Here it is 0 because mole fraction of A is 0. As the mole fraction of the A is increasing, the partial pressure is also increasing. Okay, and here at this, the mole fraction of the A is maximum, so this value is P naught A, this value is P naught B, right? Then the resultant of this is written this way, the resultant of this is this way, that is P total will be PA plus PB. Now this is the whole graph is, this line is straight, this line is straight. Not coming straight. Okay, this line is straight. This is what the graph is. This side it is vapor pressure, this side also it is a vapor pressure. Right? So this is what the ideal solution looks like. When you mix the two solutions, the graph will be this way. Now vapor pressure, now evaporation depends on what? Like we say that evaporation depends on the intermolecular forces. Intermolecular forces are less, then evaporation is more, and the intermolecular forces are more, then evaporation is less. Like for example, there is a acetone. If we consider a acetone, right? Here evaporation of the acetone is more number of the particles are found in a vapor phase. More number of the particles are found in a vapor phase. But that too for water, it is less. That too for water, it is less. Right? Why? Over here, the difference between these two is, here molecular force is hydrogen bond. Okay, here intermolecular force is what? Intermolecular force is dipole force. Now intermolecular force is a force which is existing between the molecule and which holds the molecules together. If that force is less, then evaporation will take place very easily. Means if that force is less, then molecules will leave the bulk very easily. Like why it is dipole-dipole? You take the molecules this way, one acetone molecule and another acetone molecule. There is a partial negative charge and here there is a partial positive charge. And this is what? Another acetone molecule. Partial negative charge and partial positive charge. This is one dipole, this is another dipole. Okay, so there is a attraction. There is a attraction, dipole-dipole forces. But in the case of water, what is there? This is one water molecule, and let's say this is another water molecule. What exists is a hydrogen bond force. Now, what is a hydrogen bond force? Like, what is the condition for the hydrogen bond force? That is, there should be a hydrogen in the electronegative element, provided hydrogen is connected to the electronegative element, right? That is what is exactly happening in water. Here, hydrogen is there, electronegative element is there, but hydrogen is not connected to electronegative element. That's why a dipole-dipole force, and here it is hydrogen bond force. The intensity of the hydrogen bond force is more, and dipole-dipole force is less. So here there is, since force is more, water molecule doesn't leave the bulk very easily. Here force is less, water acetone molecule leaves the bulk very easily. Note this, right? Now when you mix these two solution, right? When we mix these two solution, what happens is that there is a possibility that Raoult's law is not followed over entire range. The vapor pressure may be more than the expected or it may be less than the expected. So we come across a non-ideal solution. Non-ideal solution, I'll give you them, like for example, like ideal solution. When we talk about the ideal solution, examples will be what? Examples I'll give you of the ideal solution. When N-hexane and N-heptane is mixed. Okay, N-hexane and N-heptane. Like there is N-hexane solution, there is N-hexane. Let's say this is one N-hexane, this is N-hexane, this is N-hexane, this is N-hexane. Just showing you the molecule. What kind of force is operating over here? It is Van der Waals force. Like hexane, no? It is just Van der Waals force means it may be a dispersion or London forces which are operating between this, right? And in between N-heptane, there is also no electronegative element present, there is no polarity in both the molecules. Again, the force which is operating between N-heptane molecules are what? A dispersion or the London forces. So when you mix them, the forces of interaction, let's say this molecule was my N-hexane. So when you mix them, what is this? These are N-heptane. Okay, these are N-hexane and this is N-heptane, right? So the interactive force is same. Again, it is a dispersion force only. Means what we mean to say is that the forces of interaction between N-hexane and N-heptane is very close, and when we mix them, we get an ideal solution. Means we get this kinds of graph. There is no deviation from the molecule, right? Similarly, we can have example of the ideal solution. Like second example would be benzene and toluene. Benzene and toluene, because here also the forces of attraction will be a dispersion or the London forces, similar kind of forces, because there is no polarity, there is no electronegative element present over here. Okay, then bromoethane and a chloroethane is also an example. If you mix a bromoethane and a chloroethane, it will be also a ideal solution. Why? Bromoethane is what? We'll write this mixture of, third example I am writing, bromoethane and chloroethane. Ethane is this CH3, CH2, Br, and chloroethane is this. Now, intermolecular force which is operating between another bromoethane, and this bromoethane is what? Same, right? And here also, that too, it will be having same, because bromine and chlorine both are electronegative. The intermolecular force is operating between molecules of the bromoethane and the chloroethane is almost similar. So when you mix them also, there is no much difference in the forces which is operating. Means what we can say is that for an ideal solution, AA interaction, that is what is given in the NCERT, no? Means interaction between, when you talk about the solution, it is one molecule of the bromoethane, another bromoethane. This force is equal to one chloroethane and another chloroethane. This force, both forces are equal. And when you mix them, you get an ideal solution. Now what happens in a non-ideal solution? Non-ideal solution, we have the graphs in which the vapor pressure is slightly greater. You are expecting this and you are having this. This is a kind of positive deviation I have shown. Negative deviation, you know that it will be opposite. Now this is for a non-ideal solution. This is for non-ideal solution, right? And this is called as a positive deviation. This is a positive deviation. Non-ideal, there are two things. One is a positive deviation, and other is negative deviation. Now what does this mean? Positive deviation and negative deviation. Positive deviation means there is more evaporation in a solution phase, and negative deviation means less evaporation in a solution phase when we mix the two solutions. That is what it means. So let us discuss about the positive deviation. I'll give you an example of the positive deviation. Which mixtures shows a positive deviation? Example given over here is ethanol. Ethanol. We'll discuss about a positive deviation. Ethanol and a benzene. Ethanol and benzene. Or ethanol and cyclohexane. Now ethanol, like there is a ethanol molecules. Okay, ethanol molecules will be this way. The force of interaction existing between a ethanol molecule is what? Let's say this is one ethanol molecule, this is another ethanol molecule. What is the force which is operating? It is a hydrogen bond force which is operating over here, right? Ethanol. You mix this with a cyclohexane. Now, what will happen? Cyclohexane will come in between. Like, what kind of forces operate between one cyclohexane and another cyclohexane? It is just a van der Waals force, right, which is operating. So, if these forces, these cyclohexanes are coming in between, what happens? This is one cyclohexane, another cyclohexane, which is coming. Right? So there is a van der Waals force and that is there, but also it comes in between and it reduces this force. This force is weakened. So evaporation takes more, ethanol and cyclohexane. This is what the positive deviation. And negative positive deviation, one more example we can have is acetone. Acetone and benzene. Yes, acetone and benzene we can consider. Right, acetone there will be a dipole forces, benzene it will be just dispersion forces which will be there, and those benzene will come in between and the force which is existing between acetone and acetone, that will be reduced and it will show a positive deviation. Less intermolecular forces, more positive deviation, right? And negative deviation, there are more examples like phenol and aniline. We'll solve some questions based on this. Okay, here is the question. Question is the mixture of which shows a positive deviations from the Raoult's law. The options are given below. Options are benzene plus toluene, acetone and chloroform, and chloroethane and a bromoethane, ethanol and acetone. See, benzene and a toluene. Same kind of intermolecular force is existing. That is a dispersion force we can consider, right? Acetone and a chloroform both have same kind of force. Like acetone structure, if you see, there is no hydrogen bonding. There is partial negative, partial positive. So this forms a dipole-dipole force. And chloroform CHCl3, no, carbon CHCl3. So here also no hydrogen bond, partial negative, partial positive. A dipole-dipole force is kind of thing which will be operating over here, similar interaction. So this mixtures will be very close to ideal solution. Okay, there are no perfect ideal solution as such, but very close to ideal solution. They are not going to show any deviation. Chloroethane and a bromoethane. Like chloroethane, if you consider CH3, a dipole-dipole force, partial negative, partial positive, and here also bromoethane, a partial positive and a partial negative, right? So here also in between the molecules, dipole-dipole, here also similar. These examples will be close to ideality. But over here in the ethanol and the acetone, what kind of intermolecular force which will be existing between the ethanol molecules? Between ethanol molecule, it will be a hydrogen bond force because hydrogen is connected to oxygen, and another molecule you consider of the ethanol, the force which is existing is a hydrogen bond force, which is the strongest among all the intermolecular forces. And what about the acetone? If acetone is acetone is coming in between, this is dipole-dipole force. This is dipole-dipole force, partial negative and partial positive. So if the acetone molecules are coming in between, what will happen? They will weaken this. If acetone molecule, let's say this is the acetone molecule which is coming in between of this. This bond will be, this force will be reduced, right? So what happens? Evaporation takes place more in a mixture form when you mix ethanol and acetone. So this is the one which will show a positive deviation. Let us learn about the Henry's law over here. Henry's law. Okay, we'll take one question after that. We'll take the question. We'll write the question first. See, there is a data given. There is a gas. And the data given as argon, CO2 is there. HCHO is there, that is formaldehyde, and this is methane. And here KH value is given. Unit is Kelvin bar. Okay, KH is a Henry's constant value. The values are this way: 40.3, 1.67, 1.83 into 10 raised to minus 5 and 0.413. Okay. Question is, what is the order of the solubility? What is the order of solubility? Means solubility of gas in liquid. So which one will be more soluble and which one will be less soluble? This data is given. KH is what? KH is a Henry's constant. This is Henry's constant. Now, what does the Henry's law say? That law says that at constant temperature, solubility of gas in liquid is directly proportional to pressure of the gas, to pressure of a gas. Means it is written this way: P is equal to KH and a mole fraction, right? This is what the Henry's equation. Means this is a mole fraction of gas, mole fraction of gas. It also tells about tells about the solubility, means this value is more, means solubility is more, right? Means this value is more, means solubility is more. More the value of x, more the value of mole fraction, more is the solubility, more is the solubility, right? That is what it says. So this is the thing. So now kh, what is kh? Different gases have a different kh value, right? Kh is a function of the nature of the gas, right? Kh, Henry's constant, is a function, it is dependent on the nature of the gas, okay, and it is experimental. So here the question asked is, what is the order of the solubility? See, order of the solubility means what? If this value is high, then this should be less, right? If this is less, then this should be high to maintain that, isn't it? So what we can conclude from this law is that solubility is inversely proportional. Remember, solubility of gas is inversely proportional to Henry's constant. More is the Henry's constant, less is the solubility. What is the order of the solubility? Let's write it decreasing order we write of the solubility. So which of among this will have the maximum solubility? One which is having a least kh value, right? Decreasing will write. So it is HCHO, formaldehyde, right? This will have a maximum solubility because its value is least. After that, it is methane, then carbon dioxide, and least soluble will be argon because it is having a maximum value of kh value. So this is the thing about the Henry's law. Here in this lecture we are going to learn about the colligative properties and the abnormal molar mass. Colligative property, topic is colligative properties and abnormal molar mass. Now, abnormal molar mass is, I'll tell you what is the significance of it, and later. First, we'll understand what is a colligative property by definition. 1 minute. So, colligative property, it is a property, it is a value of which the property whose value or a property whose value depends on number of solute particles and not on the nature of particles. There are 4 colligative properties which we learn. Basically, the first is relative lowering of vapor pressure. Second, elevation in boiling point. Boiling point is increasing, so there will be what? Depression in freezing point. Depression in freezing point. And fourth is osmosis and osmotic pressure. Now, relative lowering of the vapor pressure. Now, what does this mean? Like, this is what happens. Like, whenever there is a non-volatile or there is one liquid, okay, let's consider water. Understand a concept nicely. Okay, this is water, and you know that this water boils at what? 100 degree Celsius. It is boiling at 100 degrees Celsius. Now, what I do, I mix a non-volatile solute like a glucose. I am mixing a glucose into this, and let's say certain amount of the glucose I am mixing. Let's say this was water was 500 ml, and I am dissolving something 50 gram of glucose, and you get this kind of solution. This is a solution. I will show you the different shade. This is a solution which you are getting. Now this solution is not going to boil at 100 degrees Celsius. It will be slightly higher than 100 degrees Celsius. It may be maybe 100.1 degrees Celsius, more than 100 or 100.2 degrees Celsius. Depends upon how much of the glucose you have added. More glucose you are adding, the more boiling point of the solution is going to increase. That is what it means. Now, water is having certain vapor pressure. Now, when you add a glucose to it, its vapor pressure is going to fall. So that is what it means. After adding a non-volatile solute, what is going to happen to that solvent, right? So that, see here all these concepts, all these four colligative properties are concept related to the response of the solvent, how they are changing. That is relative lowering of the vapor pressure. Elevation of boiling point, I told you. Now depression in the freezing point. You know that water is freezing, it freezes at 0 degrees Celsius. At 0 degrees Celsius, it freezing take place. So when you add a non-volatile solute, 50 gram of the glucose you are adding to a water, what will happen? The water which was freezing at a 0 degrees Celsius, it will freeze at a still lower temperature, maybe -1 degree Celsius. That is what it means. Okay. And then osmosis and osmotic pressure. Here it is a movement of the solvent through a semi-permeable membrane. Okay, we'll discuss this independently later. So we know all these things, all these concepts. What happens over here, right? So let's take one problem. Let's take one problem and we'll understand this. So this is the question. Vapor pressure of a water at 293 Kelvin is 17.535 mm of mercury. Calculate the vapor pressure of water at same temperature when 25 gram of the glucose is dissolved. Okay, it is glucose is dissolved in 450 gram of water, right? So how do we write this? Relative lowering of the vapor pressure is given this way. Let's say P naught of water solvent minus partial P naught. This is for the solution. When it is a solution, it is a partial. This is pure, right? It is in NCERT, it is, we write is like P naught A minus PA divided by P naught A. That is what we write. We can write it this way also. Let's say P naught A is the vapor pressure in a pure, and this is PA is partial. Partial is less. This is more. Since it is a lowering, this is lowering of the vapor pressure. Less vapor pressure. Relative lowering means what? We are relating it to the original one. Original was this. So This is equal to mole fraction of the B. We have this formula, right? If we slightly modify that formula, P naught A minus PA is equal to P naught A is equal to mole fraction of the B is what? Number of moles of B upon NB plus NA. See, for a dilute solution, this number of moles of B is very less in comparison to the number of moles of A. So further I write this P naught A minus PA upon P naught A is equal to NB upon NA. So what did I say? I can ignore this in front of Na. For dilute solution, number of moles of the solute, that is glucose, will be very less. So B is a solute, A is a solvent, right? So we can write it this way. So this is P naught A minus Pa upon P naught A will be what? WB. MB, number of moles is given as what? Weight of the solute upon molar mass of the solute multiplied by, I'll write it this way, molar mass of the solvent upon weight of the solvent. You can write it this way. So what we have, what values we are having? If you see P naught A is given, pure vapor pressure. How much is that? 17.535 mm mercury. PA, this is what we need to find. Weight of the solute is given to be 25 gram. Molar mass of the solute, since it is a glucose, it is what? C6H12O6. So 6 into 12 plus 12 into 1 plus 6 into 16. 72 to 12 and 96, right? 16, 6, yeah, 96. So this comes to 180. So this is given, molar mass is given to be 180. Solvent molar mass, we know that it is 18. And weight of the solvent is 450 gram. 450. So just substitute over here. So what is this P naught A? 17.3535, right? 535 minus, this is what I need to find, no? Vapor pressure of the water. Calculate the vapor pressure of water at same temperature when 25 gram is dissolved. So now this is a vapor pressure of water when 25 gram of the glucose is dissolved. This is 17.535 is equal to WB is what? 25. MB is how much? 180 into, how much is this? MA is 18 and WA is what? 450. Okay, how will solve this? That is, you can write 17.535 minus PA. This value will go over there. So 25, 18, 180 into 450 multiplied by 17.535. Okay, I'll tell you the answer directly. Answer will be like you are writing this, no? PA. PA will be finally answer is coming to 0.05 something. Partial pressure is coming to be 0.00556. Unit will be mm of mercury. This was the question. Okay, here is the question. Which among the following aqueous solutions of electrolyte will have minimum elevation in boiling point? Okay, see, elevation in the boiling point is a colligative property. Colligative property means which is dependent on a number of the solute particle, means elevation in boiling point or any colligative property is directly proportional to what? Number of the solute particle. Colligative property whether you consider elevation in boiling point, depression in freezing point, relative lowering of the vapor pressure, or osmotic pressure. All these will depend upon the number of solute particle. More is the number of the solute particle, more will be what? That particular colligative property. So colligative property, one simple rule is directly proportional to number of solute particles. More the number of the solute particle, more, like with respect to elevation and boiling point, more elevation will be there in a boiling point. But here the question is, which among the following aqueous electrolytes will have minimum elevation in boiling point, right? That is what is asked. Minimum elevation in boiling point means we need to find like MgSO4. If you are taking a MgSO4 in water, this is going to split as Mg plus aqueous and SO4 2 minus aqueous. How many particles does it give? It gives me a 2 particles. One is this and other is this. So over here, that is called as Vent-Off factor, Vent-Off factor. So that is called as I. Vent-Off factor for this is 2. Okay, initially this was 0.1, right? Now it is what? Like 0.1 moles are present in a liter. So this is what? 0.1 and 0.1 means 2 times 0.1, right? So how many moles will be there over here? 2 into 0.1, that is equal to number of moles, number of the particles. I'll write number of particles, number of moles of particles, right? Number of moles of particles over here will be 2 into 0.1, that is 0.1 plus 0.1, which is equal to 0.2, right? So 0.2 moles particle will be there. 0.2 into 6.02 into 10 to 23, these many particles. So if we get the number of moles, that will tell the relative number of the particles. In second, NaCl. When NaCl will split, it will split as a Na plus aqueous and a Cl minus aqueous in what? Water. So over here, this is 1, initially this is 1. So when it split, this is 1 and this is 1. So what is the number of moles of particle? What is the Vent-Off factor I for this? I is again 2. So hope that is coming into the frame. Yes, it is coming. So number of moles of particle, is what? 2 into 1, which is equal to 2 moles. 0.05 molar MgCl2 means 0.05 moles are molar means what? 0.05 moles per liter, right? Means there are 0.05 moles MgCl2. So this is like splitting this way, Mg2 plus and a 2 times Cl minus, means initially it is 0.05. Here it will be what? 0.05 and this is 2 into 0.05. So over here, Vent-Off factor is 3. One particle of this and 2 particle of this. So what would be the number of moles of particle? Number of moles of particle is equal to what? 0.05 plus 2 into 0.05 means it is 2 into 0.05 comes to 0.1 means 0.15 moles will be there. Last KCl will be also, you just solve this, KCl will be same as that of Mg, that will be also 0.2 moles because KCl will split as a K plus and a Cl minus. Which among this Like in which case the number of particles are least. Number of the particles are least in the case of MgCl2. That is, if you see, this is 0.2, right? Here number of the particles are 0.2 moles. Here number of the particles are 2 moles. Here number of the particles are 0.15 moles. And here the number of the particles are 0.2 moles, right? So this is the one which is having this gives the least number of the particles. See, when splitting, see, why it is giving least number of the particle? Usually it gives 3, but its concentration itself is less. That's why it is giving least number of the particles among all this. So 0.015 mole. So it will show a least elevation in the boiling point. So the answer is option C. One more question we'll do. Similar question. Here the question, which one of the following electrolytes has the same value of Van't-Hoff factor I as that of this? So we need to find Van't-Hoff factor for this and this. Then we'll match that. Like aluminum sulfate, what is the Van't-Hoff factor for this? Al2SO4 thrice. This will split as 2Al3 plus and a 3 times SO4 2 minus. So this is 2 particle, these are 3 particle. I factor for this is 2 plus 3 is equal to 5. I factor for this is 2 plus 3 is equal to 5. What about this potassium sulfate? For the A, potassium sulfate K2 SO4 will split or ionize as 2 times potassium and SO4 2 minus. Means this is 2. So I is equal to what? 2 and this is 1, which is equal to I is equal to 3, right? For this I is equal to 3. I found out that I is equal to 3. For option B, it is a complex K3FeCN6, right? When it split, only this and this is going to split. Ionized coordination pair inside, they don't dissociate. So this will be giving me this as 1 ion plus FeCN6 3 minus. So how many particle? I is equal to, this is 3 particles and this is just 1 particle. So 3 plus 1, I is equal to 4 over here. So I is equal to 4 for this. For this, what is I is equal to? For option C, what is I is equal to? AlNO3 thrice. This splits as Al3 plus 3 times NO3 minus. Means this is 1 particle and this is 3 particle. So this comes to 4. So for this also, I is equal to 4. What I want I is equal to 5. No, I guess it is this. K4FeCN6. K4, option D, FeCN6 will split as 4 potassium and FeCN6 minus 4. So this is 4 particles plus this is 1 particle. 4 plus 1, which is equal to 5. Right? So I value of this and option D is same. So the answer is option D. Okay, this is the next question. We'll solve this. Calculate a freezing point of a solution containing 60 gram of glucose in 250 gram of water. Kf for this is given. This is a question which is based on a depression in freezing point. So how does the depression in freezing point delta TF, this difference is directly proportional to molality, means more is the amount of the solute, concentration will be more and molality will be high, and this difference will be more. If this difference is more, means what? Depression is more. Like for example, like in graphical method, it is represented this way. This is the graph for the solvent. This graph is for the solvent. Okay, like this is T naught F, this is temperature, and this is, let's say, vapor pressure, right? This is what is there in the axis. This is for the solvent. Means what is a solvent? Water is a solvent, isn't it? Now, this is the graph which is shown over here. For the solution, this is the graph which will be followed. And this is the change in a phase. This is a change in a phase here. This is a change in a phase. So this is the freezing point for solution. When that solvent will change to solution, when I am putting a 60 gram of glucose into a water, that time it is going to change to a solution. Means when water was boiling at freezing at a 0 degree Celsius or a 273 Kelvin, right? 273 Kelvin, or we'll consider 0 degree, we'll deal in degrees only, that doesn't matter, 0 degree Celsius, right? So this temperature is less than 0. This is in negative. This is in negative. This temperature is in negative, right? We need to find this TF, right? So this delta is what? Delta is higher, that is T naught F minus TF, right? This is what a delta TF is. I'll write over here. Delta TF is T naught F minus TF. Once I get this delta TF, I can substitute in this case, and I know T naught F, that is 0 degree Celsius, or we can say 273 Kelvin. Okay, we'll take the temperatures in Kelvin only. We'll take the temperatures in Kelvin. Let's find delta TF first. So delta TF is equal to what? Kf molality, and also I factor is there. This is Vent off factor. Since it is a glucose, C6H12O6, this is a one molecule. This is covalent compound, and this is not going to split in water molecule. But instead, if it was like NaCl salt, if the question was same for the NaCl salt, like it was said that 60 gram of the NaCl is dissolved in 250 gram, that time I would have been 2, because this is an electrolyte, this is a salt, this splits as Na plus and a Cl minus. If it was like MgCl2, this would have been Mg plus 2Cl minus. So total 3 ions over here for the MgCl2. In that case, I would have been 3. Means if it was said that 60 gram of MgCl2 is dissolved in 250 gram. Getting? So it is this way. Now this is what the I thing is. Now let's find I anyway is equal to 1. What I'll do is first we'll find molality. First we'll find this molality, or directly also we can do delta TF is given to be how much? Kf is given to be 1.86 Kelvin kilograms per mole, right? And molality is what? Number of moles of solute. That is, I'll write it directly. That is NB upon WB, number of moles of solute upon mass of solvent in kg. Means mass of solvent will be, it will be WA, right? Since it is in kg, I'll multiply this by 1000. This is how we do it, right? So here, and into I is what? I for this is equal to 1. I for this is equal to 1. So delta TF 1.86 into number of moles of B. Number of moles of B is what? What I have done? Number of moles of B is, I should be writing this way. Just a minute. WB upon MB. I made a mistake. Sorry. Like molality is equal to what? Molality is equal to number of moles of solute upon weight of solvent. Number of moles could be written WB MB and WA as it is, right? So WB over here, weight of the solute is 60 gram, molar mass of the glucose is 180, and this is 1000, and weight of the solvent is what? 250. When you solve this answer comes to final answer comes to 2.47. Therefore delta TF is 2.47 Kelvin. This is the difference. Means T naught F minus TF is equal to how much? This difference anyway is coming to be 2.47 Kelvin. See, when it is a difference, that time it could be whether you take it in degree or a Kelvin, the difference will be same, no? 2.47. So what is TF for this? We know that this is T naught F is 0, right? And this is what? Minus TF is equal to 2.47. Therefore, TF is equal to what? Minus 2.47 degree Celsius. Means this solution will freeze at minus 2.47 degree Celsius. Earlier, it was freezing at 0 degree Celsius. The solvent was freezing at 0 degree Celsius. Hello students, welcome everyone to the revision sessions of the chapter solution. This is the lecture where I'll be discussing about the osmosis and osmotic pressure. So we'll take several examples also. I'll suggest you to note this down, whatever I'm writing, whatever I'm explaining. Always it is a good habit to note down and watch the videos. That will always help you in the long run. Okay, so osmosis and osmotic pressure, that is the topic. Osmosis and osmotic pressure. Okay, I'll not write the definitions first. I will show you the setup. Setup is this. Yes, this is the setup. And osmosis definition. Osmosis is by definition process. It is a process of movement of solvent molecules from concentration, from solution of lower concentration to solution of higher concentration. Okay, solution of lower concentration to solution of higher concentration. Understand, this is not a mixing of the two solutions. There is a semi-permeable membrane which allows only a movement of the solvent molecules. This semi-permeable membrane, this is a semi-permeable membrane, SPM, which is written, SPM will allow movement of only solvent molecules. That is what it is. Means, why only semi-permeable membrane will allow a movement of solvent molecule? You consider a solvent as a water and glucose as a solute into that. Solvent molecules are smaller in size and solute molecules are bigger. This is what the osmosis is. But concentration, in definition, if you see the process of movement of the solvent molecules from a solution of lower concentration to the solution of higher concentration. There are two things. One thing is this: you take another setup, similar kind of setup, but there is no semi-permeable membrane. There is no semi-permeable membrane, right? Semi-permeable membrane is like a filter. I'll draw a similar setup, but there is no semi-permeable membrane. Okay, and there is just one plate. Okay, which is separating two solutions. This is a divider. Let's say this is a compartment which I have, there is one compartment, right? And let's say there is a solution over here, there is a solution over here, and a solvent over here. Okay, in this case, this is a solution, high concentration, right? Here this is solvent, isn't it? If I remove this, I am not explaining osmosis over here, I am explaining a normal thing. Like, I remove this semi-permeable, I remove this plate which was there, which was separating the two solutions. Okay, now I just allow the mixing. What happens? Here concentration is high, here concentration is high, here concentration is low. The mixing will happen, right? The movement of the solute particle will move. Here there is a movement of the solute particle from higher concentration to lower concentration, till the time concentration in both the things become equal. But here it is a movement of the solvent particle, right, from concentration, from a solution of lower concentration to a solution of the higher concentration. Now why this is, how this is possible? Remember, it is a movement of the solvent particle here also from higher concentration to lower concentration, but not with respect to solution. Here higher concentration is of the solvent and lower concentration is of the solvent. Like you consider a solution and a solvent, in which case, like if you consider the equal volumes, here also there is equal volume, here also it is equal volume. Here solution means what? It is a solute, plus solvent. In same volume there is only solvent, so in which case there is a more amount of the solvent. Here this side there is more amount of the solvent, here there is less amount of the solvent. To equalize the amount of the solvent, there the movement of the solvent takes place in the side of the solution, right? And movement, this happens, level rises over here, this level will keep on rising and this level will keep on falling. This is what the osmosis, and very important, semi-permeable membrane, and it is not just a separator, right? It is not just a separator, it is the separator, but it just allows the movement of the solvent molecule because they are smaller in size compared to the solute particle, right? And here again movement is from the higher to lower, but not with respect to solution, it is with respect to solvent. Here the concentration of the solvent was more because only solvent component. Here in the same volume there was solute and the solvent, so amount of the solvent or concentration of the solvent was less in this side. To make it equal, the movement of that takes place. Now this will keep on rising, this will keep on rising till the time the concentration of the solvent, understand, solvent I am saying and not solution. The concentration means what? Amount of the solvent in both the sides become equal, right? So the minimum pressure, we will require certain minimum pressure, right, to stop this osmosis. That minimum pressure which is required to just stop the osmosis is called as a osmotic pressure. So minimum pressure which is applied to stop the osmosis, is called osmotic pressure. If you apply more pressure than osmotic pressure, what will happen? Reverse osmosis will take place. Means due to this pressure the solvent will move in this direction. Like that is, there is a different application for that. It is based on what? It will be like filtration. Application means filtration, all these processes. And this is again a solute colligative property. Why this is a colligative property? You see that there was a number of the colligative property is the colligative property which is dependent upon the number of the solute particle. You see that there was a more number of the solute particle. That's why there was less number of the solvent particle in this side. So if there are more number of the solute particle, if there is more concentration, means there will be like corresponding amount of the, not corresponding, we can say, if there is more number of the solute particle, means concentration is high, means solvent is less, and more solvent will move and more osmotic pressure will be there, right? More the concentration, more is the amount of the particle, more movement of the solvent and more osmotic pressure. You will require more pressure to stop that osmosis. So osmosis and osmotic pressure are what? Colligative properties. Let's take one example on this. Okay, let's solve this question. Calculate the osmotic pressure in pascals exerted by a solution prepared by dissolving 1 gram of polymer of molar mass 18500. Units will be what? Of this units will be molar mass is grams per mole in 450 ml of water at 37 degrees Celsius. You need to calculate the osmotic pressure. A formula for the osmotic pressure is pi is equal to CRT. C is for concentration. C is concentration Concentration of what? Concentration of solution. R is what? R is gas constant, right? Gas constant. Depending upon the units, different unit, it has different value. We'll take a unit 8.314 joules per Kelvin per mole. We'll use this value. Temperature, T is a temperature in Kelvin. Temperature in Kelvin. Right? So now there is one more factor I'll put over here. I, vent off factor. This is also very important. In this case, vent off factor, I, vent off factor is equal to what? Equal to 1. It is equal to 1. Why it is equal to 1? What is the reason? The reason is that it is a polymer. Polymer means just covalent bonding. Like salt was there. Like if I ask you, like certain gram of the magnesium chloride salt is dissolved in a water, calculate the osmotic pressure. This salt will dissociate as Mg2 plus and a 2 times Cl minus. In that case, I becomes 3 over here. You will multiply I. Okay. If you take a salt like NaCl and you put this over here, and what you get is Na plus and a Cl minus. You get I as a 2 molecules, 2 particles. Here it is 1 plus 2, 3. Here it is 1 plus 1, 2. Right? So if you take molecules like glucose, C6H12O6, you put this in water, this is not going to split. This will remain as a C6H12O6. In this case, I is equal to 1. So I will write here I is equal to 3, here I is equal to 2, here I is equal to 1. Right? You take acetic acid like CH3COOH. Right? When you put that into water, what happens is that there are many molecules of they will always dimerize. Okay, they will dimerize. How? CH3. We can take this way, COOH. There will be always a hydrogen bond between this stronger. Due to a hydrogen bonding, what will happen is that they are going to dimerize. It will be considered as a one particle. It will be considered as a one particle in that case. So here I factor will be what? I factor will be half, because 2 are getting converted to one molecule. So half. So I factor half is also possible. But that's not the question for this. I am just explaining you what is vent off factor. Here I is equal to 1 because it is a polymer. Okay. Sometimes they will write when it is written in a question, non-electrolyte, then it is I is equal to 1 always. Right. So you don't have to think. Many times in question they will mention, like if they are not giving any salts, then they will mention it is non-electrolyte. Polymer, we have to understand it is polymers are non-electrolyte. Right. So here I is equal to vent off factor, which is equal to 1. Therefore, I will modify this formula further. Pi is equal to what? Concentration. Concentration is what? Number of moles of solute upon volume of solution in liter, and we multiply this 1000 as a conversion factor. Okay. If you are writing this in ml, no, then this is a conversion factor for the liter 1000. So we'll not write this 1000, or we'll not write this 1000. Okay. I'm writing directly in liter. Whatever volume which is there, I will convert it and put over here. R is what? R is gas constant and T is this. Pi is equal to what? N number of moles is weight of the solute. WB I am writing. B is the solute, or over here that polymer is a solute. And or we'll write weight of the polymer upon molar mass of polymer. This is what the number of moles. And this is 1 by B, no? Means it could be written this way. And RT. So what will this change to formula? Weight of the polymer upon molar mass of the polymer into 1 by V into R into T. Right. So what is the weight of the polymer we have taken? It is 1 gram. Remember. It is 1 gram. What is the molar mass of polymer? Molar mass of polymer is 18500. What is the volume of solution in liter? It is 450 ml. In liter, it will be 0.450 liter. You can write 450 and multiply 1000 on the top. That also will conversion factor as a liter. R is what? 8.314 into temperature is how much? 37. 37 means how much? How many Kelvin? 27 is this, and 37 means 110 Kelvin. If you solve this, okay, let's solve this. Pi, I'll put the values. Will not take time over here. Will not spend much time. Your answer will be, if you solve this, 0.009, 0.001098. 0.001098. Now what is the unit? What are the units for this? I'll clean this part, we'll discuss with the units, because units are the important, because in units they have asked for a question, they have said that they want it in Pascals. This is what the main, otherwise you will do the substitution, right? That is very easy to do. But units are very, very important to deal with. What are the units of this answer? Pi means pressure. It was concentration. It was this. If you start, it is pi CRT. What is the concentration? Number of moles and volume in liter. So I'll write over here, it is moles and upon liter, right? Number of moles upon volume is liter. R is 8.314 joules per Kelvin per mole, and temperature is Kelvin. See, per Kelvin, Kelvin, mole, and per mole gets cancelled. So joule, liter. So your answer over here is joules per liter. Joules upon liter. See, I want to convert that liter to meter square. How will do that? Liter to meter square. So here again, make a note of this. I'll clean this part because, okay, I'll clean this part because we are doing conversion over here. That is liter. 1 liter is equal to what? 1000 ml. Can I write this 1000 ml as a centimeter cube, because 1 ml is equal to centimeter cube, right? So this is 1000. Okay, now we'll deal with this centimeter cube. 1 centimeter cube, then we'll substitute over here. 1 centimeter cube is equal to what? 1 centimeter, 1 centimeter, and 1 centimeter. Right? So what is centi? Centi is 10 raised to minus 2 meter, right? So 10 raised to minus 2, right? Meter. C stands for 10 raised to minus 2. This is 10 raised to minus 2 meter, and this is 10 raised to minus 2 meter. Right? So what is this? 10 raised to minus 6 meter cube. Means over here, if you put this centimeter cube is equal to 10 raised to minus 6 meter cube, means over here the conversion factor will be what? 1000 and 10 raised to minus 6 meter cube. I did this separately. So 10 raised to minus 6 meter cube, which is equal to, this is 10 raised to 3, which is equal to 10 raised to minus 3 meter cube, minus 6 and 10 raised to minus 3, 10 raised to minus 6 and 10 raised to 3 is 10 raised to minus 3. So over here I'll write 0.001098. This is, joule is what? Joule is Newton meter, and liter is what? 10 raised to minus 3 meter cube. So 0.001098 into 10 raised to 3 Newton meter and meter cube, this and this. So if I do this, 1.098 Newton per meter square. What is this 1.098? Newton per meter square is Pascal. Always take care of unit. Units teach you many things. Okay, units are important. Sometimes it gives you a clear direction about the concept. Units are very important. Here is the one more question which is asked based on osmosis and osmotic pressure. The following solutions were prepared by dissolving 10 gram of each in a 250 ml of water. That is glucose, urea and sucrose. 10 gram of each in 250 ml of water. Okay, write the decreasing order of the osmotic pressure. So this is P1 is the osmotic pressure due to glucose, P2 is the osmotic pressure due to urea solution, and a P3 is the osmotic pressure due to a sucrose solution. So I'll write this statement. Osmotic pressure like if the mass is same and the volume is same of the solvent, osmotic pressure is inversely proportional to molar mass. Okay, don't generalize this statement because it is applicable only when this is 10 gram. When different solution has same mass and in a same volume. Don't generalize this. I am explaining it for this question. So pi is equal to what? Pi is equal to CRT. Means pi, that is osmotic pressure pi, is directly proportional to concentration. Right? More is the concentration, more is the solute particle, more movement of the solvent. Right? So that is going to take place. So how do we write this? Number of moles upon volume into RT. Right? So this pi is number of moles could be written as what? Weight of the solute upon molar mass of the solute 1 by V RT. Now whether you consider a glucose solution, urea solution, sucrose solution, what will be constant? Weight is constant, volume is constant, R is constant, temperature is constant, right? So what is variable? Molar mass is variable of all these solutions, like because 10 gram each, no? 10 gram, this is also 10 gram, volume is also 250 ml. So we can say that pi, this is like a constant over here. Pi is equal to, it is inversely proportional to molar mass. One which is having a more molar mass will have a less osmotic pressure. So if you figure out from this, then which is having the least molar mass, because they have asked for the decreasing order of the osmotic pressure. So least molar mass will have the maximum osmotic pressure. So I think this is P2. P2 will have a least molar mass because this is, you can calculate this molar masses later. But I'll say this is P2, maximum molar mass, least molar mass, maximum osmotic pressure. Then glucose P1 and maximum molar mass, so least osmotic pressure. So this is the order in which you have to do this, right?